There is a cloud of gas drifting between two stars in the constellation Orion, and it is 700 times wider than our entire solar system. It has been there for millions of years. It is cold, dark, and almost entirely still. And somewhere inside it, right now, gravity is pulling a small knot of dust and hydrogen inward, and that knot will eventually become a star. This is how it starts, not with an explosion, not with some dramatic flash. It starts with something falling into itself slowly in silence in the dark, a clump of gas and dust in a cloud so vast that light itself takes years to cross it. Gravity finds this clump, finds that it is slightly denser than the gas around it, and begins to compress it. As the material falls inward, it heats up. Friction between particles, the pressure of collapse, these generate warmth. Over hundreds of thousands of years, the clump grows hotter, denser, and begins to glow. At this stage, it is called a protostar. It is not a star yet. It is only a collapsing ball of gas with a rising temperature at its center. For a long time, the protostar just contracts. Gravity squeezes it tighter. The core gets hotter. And then, at around 10 million degrees, something changes. At that temperature, hydrogen atoms in the core begin moving so fast that when they collide, they stick together. Two hydrogen nuclei merge, then another pair merges. Through a series of these collisions, 4 hydrogen nuclei combine to form a single helium nucleus, and in the process, a tiny amount of mass is converted directly into energy. This is nuclear fusion. It is the same process that powers the sun. It is the same process that powers every star you have ever seen in the night sky. The energy released by fusion pushes outward. It resists gravity, and at a certain point, the outward push of fusion and the inward pull of gravity reach a balance. The star stops collapsing, it stabilizes, it holds its shape. This balance has a name, hydrostatic equilibrium, but the name matters less than the idea. The idea is that a star is not a static object, it is a standoff. It is gravity and energy pressing against each other in perfect opposition, and as long as that standoff holds, the star shines. Once this balance is established, the star enters the longest and most stable phase of its life. Astronomers call this the main sequence. A star on the main sequence is simply a ball of gas fusing hydrogen into helium in its core. That is its job, that is all it does, and it can do this for a very long time. How long depends almost entirely on one thing: how much mass the star was born with. A star like our Sun, which is a fairly ordinary star in terms of size, will spend roughly 10 billion years on the main sequence. It is about halfway through that span right now. It has enough hydrogen fuel in its core to keep burning for another 5 billion years or so. It is in no rush. It burns through its fuel carefully, steadily, at a pace that allows it to shine for an almost incomprehensible length of time. But a star born with 20 times the mass of the Sun is a different kind of object. It is hotter, brighter, bluer, and far more luminous. It burns through its hydrogen at a rate that would seem reckless if stars could be reckless. A star that massive might spend only 10 million years on the main sequence. That sounds like a long time, but compared to the Sun's 10 billion years, it is 1/1000th of the lifespan. The most massive stars in the universe live fast and die young by stellar standards. They are brilliant and brief. The reason is straightforward. A more massive star has a stronger gravitational pull on its own core. To keep from collapsing, it must generate more energy. To generate more energy, it must fuse hydrogen faster. And the faster it fuses hydrogen, the sooner it runs out. So the very thing that makes a massive star so powerful, its mass, is also the thing that shortens its life. For millions of years, the star burns hydrogen in its core and everything is stable. The fusion reactions produce helium as a byproduct, and that helium accumulates at the center, like ash building up in a fireplace. The helium sits there, inert. It is too cool to fuse into anything heavier, but around it, hydrogen continues to burn. Eventually, though, the hydrogen in the core is used up. Not the hydrogen in the rest of the star, just the hydrogen at the very center, where the temperature and pressure are high enough for fusion to occur. When that core hydrogen is exhausted, the fusion reactions slow down and the outward pressure drops. Gravity, which has been patiently waiting, begins to win. The core contracts, As it shrinks, it heats up, the same principle as before. Compression generates heat, and this increasing temperature ignites a new round of hydrogen fusion, not in the core itself, but in a shell of hydrogen surrounding the helium core. Hydrogen burning in a shell around a dead core. The energy from this shell burning pushes the outer layers of the star outward. They expand enormously. The surface cools as it stretches, shifting in color from white or blue to orange and then red. The star becomes a red supergiant. If you placed one at the center of our solar system, its surface might extend past the orbit of Mars, possibly past Jupiter. These are among the largest individual objects in the universe. Betelgeuse, the bright reddish star in Orion's shoulder, is a red supergiant. It is roughly 700 times wider than the Sun. But the interior of the star is doing something much more interesting than the exterior. The core, now made mostly of helium, continues to contract and heat. When it reaches about 100 million degrees, helium atoms begin to fuse. Helium fusion produces carbon and oxygen. This is the star's second fuel source, and it burns through it far faster than it burned through hydrogen. Where hydrogen fusion sustained the star for millions of years, helium fusion lasts roughly 1 million years, an entire order of magnitude shorter. When the helium in the core is spent, the same pattern repeats. The core contracts, heats up, and ignites the next fuel, carbon. Carbon fusion produces neon and magnesium. This stage lasts about 1,000 years. Then neon fusion begins. That lasts a few years. Then oxygen fusion, which lasts a few months. Then silicon fusion, the final stage, which lasts approximately 1 day. 1 day. After millions of years of hydrogen fusion, after 1 million years of helium, after 1,000 years of carbon, the star reaches a point where its last viable fuel burns through in a single day. The acceleration is extraordinary. Each successive fuel provides less energy and is consumed more quickly. The star is running out of options at an increasing rate. By this point, the interior of the star has developed a layered structure like an onion. The outermost layer is still hydrogen. Beneath that is a shell of helium, then carbon, then neon, then oxygen, then silicon, and at the very center, the product of silicon fusion, iron. Each of these layers is a shell where a different nuclear reaction is occurring simultaneously. The star is fusing multiple elements at once, in concentric rings, with iron accumulating quietly at the core. Iron is where everything changes. Every fusion reaction up to this point has released energy. Fusing hydrogen releases energy. Fusing helium releases energy. Fusing carbon, neon, oxygen, silicon, all of these release energy. That energy is what kept the star alive. But iron is different. Iron sits at the very bottom of a curve that physicists call the nuclear binding energy curve. It is the most tightly bound nucleus. Fusing iron does not release energy, it absorbs energy. You would have to put energy in to fuse iron into something heavier, and the star has no way to do that. So iron is a dead end. It is the ash of nuclear fusion, the final waste product that cannot be burned further, and it accumulates in the core, growing heavier, generating no outward pressure at all. For a brief time, the iron core is supported by something called electron degeneracy pressure. This is a quantum mechanical effect. It comes from the fact that electrons, squeezed into a small space, resist being compressed further. It is not a thermal pressure. It has nothing to do with temperature. It is a consequence of how matter behaves at the quantum level when packed extraordinarily tight. But there is a limit to how much mass electron degeneracy pressure can support. That limit is about 1.4 times the mass of the Sun. It is called the Chandrasekhar limit, named after the physicist Subrahmanyan Chandrasekhar, who calculated it in the 1930s. Once the iron core exceeds this mass, electron degeneracy pressure fails. And then the core collapses. Not slowly, not over thousands or millions of years. The collapse happens in less than a second. The inner part of the core, a ball of iron roughly the size of Earth, falls inward at speeds approaching 1/4 of the speed of light. In a fraction of a second, that Earth-sized core compresses down to a sphere roughly 20 kilometers across, about the size of a city. During this collapse, the electrons in the core are forced into protons, creating neutrons. This process releases a staggering flood of neutrinos, tiny, nearly massless particles that interact with almost nothing. Under normal conditions, a neutrino can pass through a wall of lead a light-year thick without hitting a single atom. But in the core of a collapsing star, the densities are so extreme that even neutrinos get briefly trapped. The energy they carry is enormous. If the remaining core mass is below about 2 to 3 times the mass of the Sun, a threshold called the Tolman-Oppenheimer-Volkoff limit, the collapse halts. It halts because neutrons, like electrons before them, resist being squeezed beyond a certain density. This is neutron degeneracy pressure. The infalling material hits this wall of resistance, rebounds, and sends a shockwave racing outward through the star. This shockwave, energized by the immense flux of neutrinos, tears through the outer layers of the star, and the star explodes. This is a supernova, specifically a type II supernova or core collapse supernova. For a few weeks, this single dying star can outshine an entire galaxy of 100 billion stars. It releases more energy in those moments than the Sun will produce over its entire 10 billion-year lifetime. The outer layers of the star, all those shells of hydrogen, helium, carbon, oxygen, silicon, are flung into space at thousands of kilometers per second. And here is a detail worth pausing on. Those elements, scattered into the surrounding gas and dust, will eventually mix with interstellar clouds. Those clouds will collapse, new stars will form, planets will form around those stars. And everything on those planets, the rock, the water, the iron in the core of a world like ours, was forged inside a star that no longer exists. Every atom of carbon in your body was fused in the core of a star. Every atom of oxygen you have ever breathed was made inside a star. The calcium in your bones, the iron in your blood, these were produced either during a star's lifetime of fusion or in the seconds of a supernova explosion. This is not a metaphor. It is a factual description of where the elements came from. The periodic table is a record of stellar processes. After the explosion clears, something remains at the center. What it is depends on how much mass is left in the core. If the core remnant is below about 2 to 3 solar masses, it becomes a neutron star, one of the densest objects in the known universe. A neutron star packs more mass than the Sun into a sphere roughly 20 kilometers wide. A single teaspoon of neutron star material would weigh about 1 billion tons on Earth. These objects spin rapidly, sometimes hundreds of times per second, and can emit beams of radiation from their magnetic poles. When those beams sweep past Earth like lighthouse beacons, we detect them as pulsars. But if the core remnant exceeds the 2 to 3 solar mass threshold, if there is simply too much mass for even neutron degeneracy pressure to resist, then nothing stops the collapse. No known force in physics can halt it. The core continues to fall inward, past the neutron star stage, past any known state of matter, and it becomes something else entirely. It becomes a black hole. A black hole is not a hole. It is not an empty space. It is not a tear in the fabric of the universe, though that description gets used often enough. A black hole is an object, a region containing mass, where gravity has become so strong that nothing can escape it. Not matter, not radiation, not light. The gravitational pull within this region exceeds the speed of light, and since nothing in the universe can travel faster than light, nothing gets out. The boundary of this region is called the event horizon. It is not a physical surface. There is no wall, no membrane, no edge you could touch. It is simply the distance from the center at which the escape velocity equals the speed of light. Cross inside this boundary, and you are committed. There is no trajectory, no speed, no engine that will carry you back out. The event horizon is the point of no return, defined by mathematics, not by material. The size of the event horizon depends on the mass of the black hole, and the relationship is simple: more mass, larger horizon. The relevant distance is called the Schwarzschild radius, named after Karl Schwarzschild, who worked out this solution to Einstein's field equations in 1916, only months after Einstein published his theory of general relativity. For a black hole with the mass of our Sun, the Schwarzschild radius is about 3 kilometers. The entire mass of the Sun, compressed into a sphere 6 kilometers across. For a black hole with 10 times the Sun's mass, the radius is about 30 kilometers. At the very center of the black hole, general relativity predicts something called a singularity. This is the point where all the mass has collapsed to a location of theoretically infinite density and zero volume. The known laws of physics break down at the singularity. The equations produce infinities, which is usually a sign that a theory has reached the edge of what it can describe. Most physicists suspect that a more complete theory, one that unifies general relativity with quantum mechanics, would replace the singularity with something else. But we do not have that theory yet. So the singularity remains a mathematical statement that something extraordinary is happening at the center, something our current understanding cannot fully explain. Between the event horizon and the singularity, everything that has ever fallen into the black hole is on its way inward. There is no stable orbit inside the event horizon. There is no hovering. The geometry of spacetime itself is curved so severely that every possible direction, forward, backward, sideways, points toward the singularity. Time and space, in a sense, trade roles. Moving through space toward the singularity becomes as inevitable as moving forward through time. Outside the event horizon, things are different but still strange. Just beyond the event horizon is a region called the photon sphere. It sits at 1.5 times the Schwarzschild radius. At this distance, gravity is strong enough that light photons can travel in circular orbits around the black hole. A beam of light aimed sideways at exactly the right distance would loop all the way around and come back to where it started. But these orbits are unstable. The slightest disturbance sends the photon spiraling inward past the event horizon or escaping outward into space. The photon sphere is part of what creates the distinctive visual appearance of a black hole. When the Event Horizon Telescope collaboration released the first image of a black hole in 2019, the supermassive black hole at the center of galaxy M87, the bright ring surrounding the dark center, was not the event horizon itself. It was light from the accretion disk, bent and magnified by the extreme warping of spacetime near the photon sphere. The dark shadow at the center was the event horizon's silhouette, roughly twice as large as the event horizon itself, because of how spacetime bends the surrounding light. The accretion disk is often the only way we can detect a black hole at all. When a black hole exists near a source of matter, a companion star, a cloud of gas, the dense core of a galaxy, that matter can be gravitationally captured. It does not fall straight in. Instead, it spirals inward, forming a flattened, spinning disk of material called an accretion disk. As the material in the disk spirals closer to the event horizon, it moves faster. Friction between particles in the disk heats the gas to extreme temperatures, millions of degrees. Material this hot emits X-rays, which are detectable by space-based telescopes. This is remarkably efficient. The process of matter falling into a black hole and converting gravitational energy to radiation releases about 10% of the mass energy of the infalling material. That might not sound impressive until you compare it to nuclear fusion, which converts about 0.7%. Accretion onto a black hole is roughly 14 times more efficient than the process that powers stars. It is one of the most efficient energy release mechanisms in the known universe. Some black holes also produce jets, narrow beams of particles fired outward from the poles at speeds approaching the speed of light. These jets can extend for hundreds of thousands of light years, far beyond the galaxy that contains the black hole. The exact mechanism that produces them is still not fully understood, though it likely involves the interaction of magnetic fields with the spinning accretion disk and possibly the rotation of the black hole itself. The jets from supermassive black holes are among the most energetic phenomena in the universe. And then there are the effects on time. Near a black hole, time passes differently depending on where you are. This is not a metaphor or a thought experiment. It is a measurable physical consequence of general relativity. A clock placed near a black hole in a region of strong gravity ticks more slowly than an identical clock placed far away in a region of weaker gravity. This effect is called gravitational time dilation. It happens everywhere gravity exists, including here on Earth, where clocks at sea level tick slightly slower than clocks on mountaintops, but near a black hole, the effect becomes extreme. If you watch someone falling toward a black hole from a safe distance, you would see them appear to slow down as they approached the event horizon. Their movements would become sluggish. The light they emitted would shift toward the red end of the spectrum, a phenomenon called gravitational redshift, and grow dimmer. They would seem to freeze at the edge of the event horizon, fading from view, never quite crossing it. From your perspective, they would take an infinite amount of time to reach the boundary. But from the falling person's own perspective, nothing unusual happens at the event horizon. They cross it without fanfare. The event horizon is not a wall or a barrier. It is a boundary defined by the behavior of light, and for someone falling through it, the experience is smooth. They would not feel anything special at the moment of crossing. What happens afterward, though, is a different matter. Inside a stellar mass black hole, the tidal forces are severe. Because gravity follows an inverse square law, its strength increases sharply as distance decreases. The gravitational pull on the near side of an object is significantly stronger than the pull on the far side. If a person were falling feet first into a stellar mass black hole, the gravity at their feet would be noticeably stronger than the gravity at their head. This difference would stretch them vertically and compress them horizontally. The effect has been given a name that is both descriptive and slightly grim: spaghettification. The object is stretched and thinned, like a strand of pasta, by the growing difference in gravitational force across its length. For a stellar mass black hole, one with perhaps 10 times the mass of the Sun, spaghettification would begin well before the person reached the event horizon. The tidal forces at 30 kilometers from the center of a 10 solar mass black hole are already fatal. For a supermassive black hole, the situation is counterintuitively different. A supermassive black hole with millions or billions of solar masses has an event horizon that is proportionally much larger. The Schwarzschild radius of a 4 million solar mass black hole like Sagittarius A star, the one at the center of our galaxy, is about 12 million kilometers. At that scale, the tidal forces at the event horizon are remarkably gentle. A person could theoretically cross the event horizon of a supermassive black hole without being torn apart, without even noticing. The spaghettification would come later, deeper inside, as they fell closer to the singularity. This is one of those facts about black holes that seems backward at first. The larger the black hole, the less violent the experience of crossing its boundary. The smaller the black hole, the more extreme the tidal forces at its edge. It follows from the mathematics, but it goes against the instinct that bigger should mean more dangerous at the surface. There is also the matter of what a black hole does to light passing near it, not light that falls in, but light that passes close enough to be bent without being captured. Massive objects warp the fabric of spacetime around them. This warping curves the paths that light follows, an effect called gravitational lensing. Near a black hole, this lensing is dramatic. Light from stars or galaxies behind the black hole is bent around it, sometimes forming arcs or rings. The accretion disk, if one is present, appears distorted when viewed from most angles. Light from the far side of the disk is bent over the top and under the bottom of the black hole, creating a warped, asymmetric image. One side of the disk appears brighter than the other because the material spinning toward the observer is blue-shifted and amplified, while the material spinning away is redshifted and dimmed. All of this, the event horizon, the singularity, the photon sphere, the accretion disk, the time dilation, the tidal forces, the gravitational lensing, exists around every black hole. But black holes themselves come in different sizes, and those sizes span an almost incomprehensible range. The stellar mass black holes that form from dying stars are the most common type. They range from about 5 to perhaps 100 times the mass of the Sun, though most of the ones we have detected fall between 5 and 20 solar masses. Their event horizons are small by cosmic standards, tens to hundreds of kilometers across. They are scattered throughout galaxies. The Milky Way alone may contain 100 million of them, drifting through the galaxy in the dark, invisible unless they happen to be near something that reveals their presence. At the other end of the scale are the supermassive black holes. These sit at the centers of most large galaxies, possibly all large galaxies. Their masses begin in the hundreds of thousands of solar masses and extend to billions. The black hole at the center of our galaxy, Sagittarius A star, has about 4 million times the mass of the Sun. The one at the center of the galaxy M87, the first black hole ever directly imaged, has roughly 6.5 billion solar masses. These are objects whose event horizons are comparable in size to the orbits of planets. The Schwarzschild radius of the M87 black hole is about 19 billion kilometers, larger than the orbit of Pluto. One of the strangest facts about supermassive black holes is that their average density, their mass divided by the volume within their event horizon, can be surprisingly low. A black hole with 1 billion solar masses, for instance, would have an average density less than that of water, less than the density of the air in this room in some extreme cases. This does not mean the black hole is diffuse or empty. All the mass is concentrated at or near the singularity. But if you were to spread that mass evenly throughout the volume enclosed by the event horizon, the resulting density would be unremarkable. This is because the event horizon grows linearly with mass, but volume grows as the cube. So as mass increases, the volume enclosed by the event horizon increases much faster and the average density drops. How supermassive black holes formed in the first place is still an open question. Some of the most massive ones have been observed in galaxies that existed less than 1 billion years after the beginning of the universe, which raises a puzzle. 1 billion years may not have been enough time for a stellar mass black hole to grow through ordinary accretion of surrounding gas into something millions of times the mass of the Sun. Several ideas have been proposed: the direct collapse of enormous gas clouds in the early universe, the rapid merging of many smaller black holes in dense stellar environments, but no single explanation has been confirmed. Between the stellar mass and the supermassive, there is a gap. Theoretically, black holes with masses between a few hundred and 100,000 solar masses should exist. These are called intermediate mass black holes, and they have been very difficult to find. A handful of candidates have been identified in globular clusters and in the outskirts of some galaxies, but definitive confirmation remains scarce. The search for these middleweight black holes is ongoing, and finding them would help explain how the smallest black holes might grow into the largest ones over cosmic time. The difficulty with detecting any isolated black hole is obvious. They emit no light. A black hole sitting alone in space, with no nearby matter to pull in and heat up, is essentially invisible. It reveals itself only through its gravitational influence on things around it. The first strong evidence for a black hole came in 1971 from an X-ray source in the constellation Cygnus called Cygnus X1. A massive blue star in that system appeared to be orbiting something invisible, and X-rays were being emitted from a disk of hot gas spiraling toward the unseen companion. The invisible object's mass was estimated at more than a dozen solar masses, far too heavy to be a neutron star. The inference was that it had to be a black hole. The X-rays were coming not from the black hole itself, but from the superheated accretion disk of gas being torn from the companion star. This method, observing the gravitational effects of a black hole on visible companions, has been refined considerably. At the center of our own galaxy, astronomers tracked individual stars orbiting Sagittarius A star for years, plotting their paths with extraordinary precision. Some of these stars complete their orbits in just a few decades, which is remarkably fast for objects orbiting something 4 million times the mass of the Sun. The orbital data made it possible to calculate the mass of the central object with high confidence. This work, carried out primarily by Andrea Ghez and Reinhard Genzel and their respective teams, earned a share of the Nobel Prize in Physics in 2020. Gravitational waves opened an entirely different way of detecting black holes. In September 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the signal of 2 black holes spiraling into each other and merging. These 2 objects had masses of about 36 and 29 times the mass of the Sun. As they orbited each other at closer and closer range, moving faster and faster, they sent ripples through the fabric of spacetime itself. Those ripples, gravitational waves, traveled outward at the speed of light, and more than 1 billion years later passed through Earth, where they stretched and compressed space by a fraction of the width of a proton. LIGO detected this. The merged black hole that resulted had about 62 solar masses. The remaining 3 solar masses had been radiated away as gravitational wave energy, pure spacetime vibration, carrying mass energy into the universe. This detection confirmed a prediction Einstein had made 100 years earlier, but thought might never be measured. Gravitational waves were real, black hole mergers were happening, and we now had a way to observe the universe not through light, but through the vibrations of spacetime itself. And in April 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole, the one in M87. The image showed a dark central shadow surrounded by a bright, slightly asymmetric ring of light. The shadow was the silhouette of the event horizon against the glow of the accretion disk. The asymmetry of the ring was caused by the rotation of the disk. The side moving toward us appeared brighter due to relativistic beaming, while the receding side appeared dimmer. 2 years later, in May 2022, the same collaboration released an image of Sagittarius A star, the much smaller supermassive black hole at the center of the Milky Way. These images were not photographs in the traditional sense. They were reconstructed from radio wave data collected by telescopes spread across the globe, synchronized to function as a single Earth-sized instrument. The resolution required to image a black hole is extraordinary. It has been compared to reading the date on a coin in Los Angeles from a vantage point in New York. The achievement was as much one of engineering and computation as it was of astronomy. The existence of black holes connects to something much larger than the death of a single star. When a massive star explodes as a supernova, the heavy elements it forged during its lifetime, and the even heavier elements produced in the explosion itself, are scattered into the surrounding interstellar medium. This material mixes with the gas and dust already drifting between stars. Over millions of years, gravity gathers this enriched material into new clouds, and new stars begin to form within them. Planets form in the disks of gas and debris around those new stars. And the atoms in those planets, in the oceans on those planets, in the organisms that might one day arise on those planets, trace their origins back to the cores and explosions of stars that ceased to exist long ago. This cycles stars forming from gas, fusing heavier elements in their cores, dying and returning those elements to the gas from which new stars form, has been repeating since the first generation of stars formed in the early universe. The first stars were made almost entirely of hydrogen and helium, the 2 lightest elements, because those were the only elements that existed after the initial expansion of the universe. Those first stars lived, fused heavier elements, died, and seeded their surroundings with carbon, oxygen, nitrogen, silicon, iron. The second generation of stars incorporated those heavier elements, and the process continued, generation after generation, each one a little more chemically complex than the last. The Sun is not a first-generation star. It contains elements that could only have been produced inside earlier stars that no longer exist. The Earth, which formed from the same cloud of gas and dust as the Sun, is rich in iron, silicon, oxygen, carbon, all of which required stellar fusion or supernova conditions to create. The raw material of the planet beneath us and of the bodies we carry was processed through the interior of at least one star, and possibly several, before it became part of the solar system. Black holes are the final state of the most massive contributors to this cycle. The stars that die as black holes were, during their lifetimes, among the most prolific producers of heavy elements. Their supernovae were among the most energetic dispersal events in the universe. In a sense, black holes mark the places where the most generous stars once burned, the ones that gave the most material back before gravity claimed what was left. At the centers of galaxies, supermassive black holes play a different kind of role. They influence the behavior of matter across tens of thousands of light years. When a supermassive black hole is actively consuming matter, when it has a bright accretion disk and powerful jets, the energy it releases can heat surrounding gas to the point where it cannot collapse to form new stars. This feedback mechanism may help regulate the rate of star formation in galaxies. There is a well-established correlation between the mass of a galaxy's central black hole and the motion of stars in the galaxy's central bulge. The bigger the black hole, the faster the stars in the bulge are moving. This suggests a deep connection between the growth of a galaxy and the growth of the black hole at its center, though the precise nature of that connection is still being studied. Galaxies merge with each other over cosmic time. When they do, their central black holes eventually find each other, spiral inward through the merged galaxy, and coalesce. The gravitational waves produced by supermassive black hole mergers would be far too low in frequency for LIGO to detect, but future space-based observatories are being designed to listen for them. These mergers would produce ripples in spacetime strong enough to be detected across the observable universe. In 1974, the physicist Stephen Hawking proposed something that seemed to contradict the very definition of a black hole. Using the framework of quantum mechanics applied to the curved spacetime near an event horizon, he showed that black holes should emit a faint glow of radiation. This has come to be called Hawking radiation. The mechanism is subtle. It involves the behavior of quantum fields at the boundary of the event horizon, where pairs of virtual particles are constantly forming and annihilating. Near the event horizon, one particle of such a pair can fall in while the other escapes, carrying energy away from the black hole. Over time, this process causes the black hole to lose mass. For any black hole we have actually observed, this radiation is negligibly small. A stellar mass black hole would take far longer than the current age of the universe to evaporate through Hawking radiation. The timescale is roughly 10 to the power of 67 years for a black hole with the mass of the Sun. The universe is about 13.8 billion years old. These are not comparable numbers, but the principle matters. It means that black holes are not eternal. Given enough time, even a black hole will fade. The temperature of a black hole's Hawking radiation is inversely proportional to its mass. The more massive the black hole, the cooler its radiation, and the slower it evaporates. Smaller black holes are hotter and radiate more quickly. If a black hole were to shrink to a very small mass, it would become extremely hot and radiate intensely in its final moments, though no such event has ever been observed. Hawking radiation remains a theoretical prediction, widely accepted by physicists, but not yet confirmed by direct detection. There is a question buried in Hawking radiation that remains unanswered, and it is one of the more significant unresolved problems in physics. When matter falls into a black hole, the information it carried, the specific arrangement of particles, the quantum states, the details that made it what it was, appears to be lost behind the event horizon. But quantum mechanics holds that information cannot be destroyed. If Hawking radiation is purely thermal, carrying no information about what fell in, then either general relativity or quantum mechanics must be incomplete. This tension is known as the black hole information paradox. Many proposed solutions exist, but none has been definitively established. The black holes that formed from the first massive stars are still out there. They have been drifting through their galaxies for billions of years, occasionally merging with other black holes, occasionally capturing stray gas, growing slowly or not at all. Some are in binary systems, locked in orbit with companion stars. Some are solitary, drifting through the void between stars, detectable only if something happens to pass close enough to reveal their gravitational pull. Some sit at the centers of galaxies, having grown to millions or billions of solar masses through billions of years of accretion and merger. And the process that created them continues. Somewhere in the Milky Way right now, a massive star is nearing the end of its fuel. Its core is layered with the products of successive fusion reactions. Iron is accumulating at the center. In a few thousand years, or a few hundred, or perhaps less, the core will exceed the Chandrasekhar limit. It will collapse. The star will explode, and something will be left behind in the dark, either a neutron star or a new black hole, depending on the mass. The raw material for that star came from older stars, and the elements scattered by its explosion will become part of newer ones. The cycle has no beginning that we can identify with certainty, and it has no foreseeable end. Stars form, burn, die, and return their substance to the medium from which the next generation emerges. Black holes are where that cycle reaches its most extreme conclusion, where gravity gathers enough mass and enough density that the collapse becomes permanent, and what falls in does not come back. The clouds of gas in the space between stars carry the remnants of every stellar generation that came before. They are enriched with carbon and oxygen and silicon and iron, with elements heavier than iron that were forged in the moments of supernova explosions. These clouds drift and collide and compress, and within them, gravity begins again what it has been doing since the beginning, pulling matter together, heating it, and building something new from what was left behind. A star that forms today, in one of these enriched clouds, carries inside it the history of many earlier stars. Its composition is a record. The metals in its atmosphere, the ratios of isotopes in its outer layers, the particular mixture of elements in the disk of material orbiting around it, all of these are traces of the stars that came before. Each new star is made from the ashes of older ones, and each will eventually return its own processed material to the interstellar medium. The ones with enough mass will leave behind neutron stars or black holes. The ones without enough mass will shed their outer layers as planetary nebulae and leave behind white dwarfs, dense, cooling remnants about the size of Earth, slowly fading over billions of years. The universe is about 13.8 billion years old, and in that time, several generations of stars have lived and died. The heaviest elements we find on Earth and throughout the solar system required multiple cycles of stellar birth and death to accumulate. The gold in the Earth's crust, for instance, is thought to have been produced primarily in neutron star collisions, events even more extreme than supernovae, where the densities and temperatures were sufficient to build nuclei that heavy. These collisions scattered their products into the gas from which our corner of the galaxy eventually condensed. All of this proceeds at its own pace. Stars that will burn for trillions of years are only now in the early stages of their main sequence lives. The smallest, coolest red dwarf stars in the Milky Way have barely used any of their hydrogen. They will still be burning long after the sun has exhausted its fuel, swollen into a red giant, shed its outer layers, and contracted into a white dwarf, long after Sagittarius A star has consumed whatever stray gas drifts close enough. Long after the galaxies in our local group have merged into a single larger structure. The timescales involved stretch beyond any useful comparison to human experience. 1,000,000 years is a long time in any context that matters to a person, but 1,000,000 years is a small fraction of the life of even a moderately massive star, and it is an insignificant sliver of the time that the smallest stars will continue to burn. The universe operates on timescales that make even geological time feel brief. And within that expanse, the black holes persist. They are among the most long-lived structures in the universe. A stellar mass black hole, sitting quietly in the dark, consuming nothing, will outlast the stars around it. It will outlast the galaxy that contains it, if the galaxy eventually disperses. It will sit in the dark, slowly, almost imperceptibly radiating its mass away through Hawking radiation, growing smaller over timescales that have no practical meaning. 10 to the 67th years, 10 to the 100th years, numbers so large that writing them out in full would fill pages. Eventually, if Hawking's calculations are correct, even the black holes will be gone. The last one will radiate its final quantum of energy and vanish. But that moment is so far in the future that the current age of the universe, all 13.8 billion years of it, would not register as a measurable fraction of the time remaining. For now, the black holes are here. They were made from the cores of the most massive stars, through a process that began with gravity pulling on a clump of gas in a cold, dark cloud, and ended with that gas collapsing past every known limit. They are dense, dark, and patient, and the space around them is still filled with the material that their parent stars once forged: carbon, oxygen, iron, drifting quietly through the galaxy, waiting to become part of something new. There is a particular kind of simplicity to all of this once you step back far enough. A cloud of gas collapses, it becomes a star. The star burns through its fuel one element at a time, building heavier and heavier atoms in its core. If the star is massive enough, it reaches iron and the process stops. The core falls inward. The outer layers are thrown outward. What remains at the center either becomes a neutron star or a black hole, depending on how much mass is left. And the material that was thrown outward mixes with the gas between stars, enriching it, so that the next generation of stars and planets will have more to work with than the one before. The steps are the same every time. The details change, the mass of the star, the speed of its fusion, the specific elements it produces in its layered interior, the violence of its ending, but the sequence is the same. Gravity gathers, fusion resists, fuel runs out, gravity wins, something is left behind and something is given back. The black holes that remain are the densest remnants of the densest cores. They carry within them the mass of what was once a burning, luminous star, compressed into a region of spacetime from which nothing returns. But they are not active participants in the cycle anymore. They sit at the end of the process, gravity's final claim, while around them, the galaxy continues its slow work of forming new stars from old material. In the spiral arms of the Milky Way, molecular clouds stretch across dozens of light years, dense and cold and dark. Within them, small regions of higher density begin to collapse. The collapse takes hundreds of thousands of years. The protostar at the center heats up. Eventually, fusion begins. A new star joins the main sequence. It will burn for however long its mass allows, billions of years if it is small, millions if it is large. And when it dies, it will return most of its mass to the interstellar medium, keeping only what gravity holds onto at the center. This has been happening for more than 13 billion years. The first stars formed a few hundred million years after the universe began, when the gas that filled all of space had cooled enough and clumped enough for gravity to pull it into dense pockets. Those first stars were made entirely of hydrogen and helium because nothing heavier existed yet. They were massive, hot, and short-lived, and when they died, they created the first heavy elements and possibly the first black holes. Everything that followed, every subsequent generation of stars, every planet, every grain of dust, carries their legacy in its composition. The iron at the center of the Earth was once inside a star. The oxygen in the atmosphere was fused from carbon in a stellar core. The calcium that forms the structure of bones was produced in the final burning stages of a massive star or in the explosive shock of a supernova. None of this material was always here. It was all made, atom by atom, through processes that took millions of years inside objects that no longer exist. The raw materials of the world were assembled in furnaces that burned out long before the sun ignited. And the black holes that ended those furnaces are still present in the galaxy, carrying mass that was once part of those original stars. They do not shine, they do not fuse, they do not give anything back, except for the faint theoretical whisper of Hawking radiation, so slight that it has never been measured. They are gravity's collection, held in the dark, while the universe around them continues to rearrange the elements that earlier stars created. In a quiet part of the galaxy, far from the central black hole, far from any active star-forming region, a stellar mass black hole orbits the galactic center just as the stars around it do. It follows the same gravitational path. It obeys the same laws. It simply does not shine. It has no surface, no atmosphere, no warmth. It is 10 or 15 times the mass of the sun, compressed into a sphere a few dozen kilometers across, and it has been here for billions of years. It will be here for billions more, long after the stars nearest to it have burned through their fuel and gone dark themselves. The space between stars is not truly empty. It contains a thin scattering of gas and dust, roughly 1 atom per cubic centimeter in most regions, though the density varies. This material is threaded with magnetic fields, illuminated faintly by starlight and stirred by the shockwaves of distant supernovae. It is the medium from which all stars are born and to which most stellar material is returned. It is the connective tissue of the galaxy, the reservoir from which gravity draws and to which death gives back. Within that medium, the elements produced by billions of years of stellar fusion drift and mix. Hydrogen, the simplest and most abundant element, makes up roughly 75% of the visible matter in the universe. Helium accounts for most of the rest. The heavier elements, everything from carbon to uranium, make up less than 2% of the total. But that 2% includes everything that makes rocky planets, liquid water, and complex chemistry possible. Every atom of that 2% was forged inside a star. Some of those atoms have been through more than one stellar cycle. An atom of carbon produced in a star 8 billion years ago might have been expelled in that star's death, incorporated into a molecular cloud, drawn into a new star, fused into oxygen, and expelled again. The same atom might have been part of 3 or 4 different stars, before becoming part of the cloud that formed the sun and its planets. The history of a single atom can span the majority of the universe's existence, passing through multiple stellar generations, spending time as interstellar gas, as part of a planet, as part of a living thing, and perhaps one day as part of a star again. Black holes are where some of those atomic histories come to an end. An atom that crosses the event horizon of a black hole does not return to the interstellar medium. It does not become part of a future star or a future planet. Its journey, at least as far as the rest of the universe is concerned, is over. The mass remains, adding to the black hole's gravitational pull, but the specific identity of what fell in, the particular element, the particular configuration of protons and neutrons and electrons, is lost behind the horizon. Whether that information is truly destroyed or merely hidden is one of the questions that physics has not yet answered. The night sky, seen from a place far from city lights, shows a few thousand stars to the unaided eye. Each of those stars is at a different stage of its life. Some are young, still burning through their hydrogen on the main sequence. Some are older, already swelling into red giants or beginning to fuse helium. A few are near the end, their cores heavy with the products of advanced fusion. And scattered among them, invisible, are the remnants of stars that have already died, white dwarfs, neutron stars, and black holes, each one carrying the compressed remains of what was once a bright and burning object. The galaxy turns slowly, carrying all of them, the living stars and the dead ones, the clouds of gas and the black holes, the planets and the dust, around a common center. One full rotation takes about 230 million years. The Sun has completed roughly 20 orbits since it formed. The galaxy has completed perhaps 50 or 60 rotations since the first stars ignited within it. And within that slow rotation, the cycle continues. Gas collapses into stars. Stars fuse lighter elements into heavier ones. Stars die and scatter their products. New stars form from the enriched material. The most massive of them collapse into black holes when they are done, and the elements they forged, the carbon, the oxygen, the silicon, the iron, remain in the galaxy, part of the long, quiet process of building complexity from simplicity, one stellar generation at a time. The clouds of gas drift between the stars, carrying those elements with them, cold and dark, and waiting for gravity to begin the process once more.